Hello everyone, I'm Priyanka. I'm a PhD student at Georgia Institute of Technology, and in this presentation, I'm going to be talking about ferroelectric field effect transistor reliability. Specifically, I'm going to be talking about a relatively less discussed phenomenon in these devices, and that is the first right pulse induced interface damage in FEFETs. So the results that we see after evening testing, they tell us that the very first right pulse applied to a ferroelectric field effect transistor, that is to a pristine fabricated device, actually contributes to about 50% of the damage seen throughout its lifetime. So before we go into the details of this results, let us go to the basics of the material, that is, what is ferroelectricity? So these are non-centrosymmetric crystal structure materials. That is, if you have a crystal structure that looks like this, if the center atom is pointed upwards, we have the upward polarization, and if the center atom is pointed downwards, we have the downward polarization. And we can sandwich this material between two metal electrodes and apply an electric field and switch the polarization between the two states. And that's how we get this hysteresis loop over here. And these materials that are ferroelectrics have garnered significant attention in the last decade. And if we look at this memory spectrum over here, we have access time on the y-axis, density on the x-axis. And we have low density but high access speed SRAM. And on the other end, we have NAND with low access speeds but high density. And there are gaps in this memory spectrum. And emerging memory technologies like ferroelectric FETs or ferroelectric capacitors can bridge these gaps and help enable better compute. So we have the ferroelectric FET that can act as ferroelectric NAND, and we also have the ferroelectric FET acting as non-volatile SRAM applications, and we also have the ferroelectric capacitor for non-volatile DRAM applications. In this talk, I'm going to be specifically talking about ferroelectric field effect transistors. So let's look at the basic operation of these devices. Here I have a schematic of a ferroelectric FET. We have the ferroelectric layer, an interfacial layer, which is silicon dioxide in most cases, and we have the silicon substrate over here. And the mechanism that I'm going to be explaining is for N-channel FEFETs. So if we now apply a positive program pulse to this device, the polarization will point downwards, leading to the positive polarization charges being close to the channel. And that gives us the low VT state. Now, if we apply a negative erase pulse to this gate of this device, the polarization points upwards, leading to the negative polarization charges being close to the channel, making it harder to invert the surface. That gives us the high VT state. Now, between the low VT state and high VT state is the memory window of this device. Now, these devices face three key reliability challenges, and those three are named memory window closure, read after write delay, and gate leakage. So I'll briefly explain what these three are. First, we have memory window closure. As we saw, we have a memory window for these devices, and when we apply bipolar stress cycling to these devices, which emulate repeated writing to these devices, that gives us an initial memory window, but as we cycle the device, that leads to the memory window reducing. And eventually, this memory window closes down to 0. So this is the memory window closure issue, and this is a significant issue for ferroelectric field effect transistors. Now, if we look at the read after write delay effect, we have the write operation performed, and after this, we need to provide a certain amount of time before we can read the device again. So that is the read after write delay effect. And initially, say we have a 1 microsecond delay, we will see a certain memory window. And as we increase the read delay, we will see that the memory window opens up. So this is the read after write delay effect. We need the time to be as less as possible, but we need to provide some time to be able to read the maximum memory window in these devices. We also have gate leakage. Here we perform a standard IGVG measurement, and here is a schematic of the gate leakage. Initially, we have some gate leakage in the precision fabricated state, and as we cycle the device with bipolar cycling, we see that the leakage increases. So we saw that these three are the key reliability challenges faced by these devices, and in this talk, I'm going to be specifically talking about one of these issues, which is memory window closure. So what's generally understood about memory window closure is that we have the ferroelectric layer with the ferroelectric dipoles, Then we have the interfacial layer with a certain number of traps, and we have the substrate over here. Initially, in the as fabricated state or in the initial state, we have certain number of traps and we have a certain number of polarization. And most of this polarization is actually screened by this traps present over here, and we see only the remaining charges over seen being reflected in the channel layer. Now, as we cycle the device, this IL charges now increases, leading to full screening of these polarization charges. Now, that leads to lesser amount of charge being seen in the channel. That leads to the memory window closing down. So, initially, this polarization is partially screened, giving us some memory window, but after cycling, the IL traps increases, screens more of the polarization, and leads to a memory window closure. Now, what's less discuss and what we're going to talk about in this particular presentation is the first switch degradation. What we see is that from the fabricated state to the very first pulse applied, there is actually a significant generation of traps. So let's go into the details of this. In order to understand this mechanism, we've taken two different devices. One is what we call the FEFET and one is what we call the MOSFET. So here is the brief fabrication steps for these devices. And what we do here is we have a crystallization step that converts this hetero layer into a ferroelectric layer, and it has a crystal structure over here. And over here we have the MOSFET. It has the same hetero layer, but the crystallization step is not present, leading to an amorphous dielectric layer. So if we look at the capacitance versus voltage characteristics over here, we see that the effective oxide thickness is roughly the same for both these devices. What that now allows us to do is directly compare the voltages across these devices. So we know that when we apply a certain voltage across these two devices, the electric field applied across these devices are going to be the same. Now, if we look at the PV loops, that's the polarization versus voltage curves, we clearly see that the FEFET has a polarization loop and the MOSFET has a dielectric response. And if we look at the memory window versus voltage curves, we see that the FEFET has a memory window, that is a voltage dependent memory window, and at 3.5 volts we see about 1.5 volts memory window, while the MOSFET shows zero memory window for all right voltages. So now these are the devices that we have. Now let's get into the experimental details. So now let us apply bipolar stress to these devices. Initially, we have the pristine, that is as fabricated device, and we now perform a read operation. The thing to note here is that before this read operation, there is no kind of voltage applied to this device. It is simply just the as fabricated state. So when we perform this read operation, here is the IDVG curve that we see. We see that we have a sharp SS and that is plotted over here. In initial state, we have a low SS value of about 70 or 80 millivolt per decade. Now, let us apply one particular voltage pulse to this device. So we apply one cycle to this device and then perform the same read operation. And that now gives us the memory window because we're performing read operation in the positive and negative direction, that is with arrays and program pulses. So that gives us the arrays and program state with the memory window. But now if we look at the subthreshold slope of this device, now that gives us a much higher value. So between the very first right pulse and the second pulse, we see that there is a significant jump in the degradation. So SS goes from about 70 to 80 millivolt per decade to about 250 millivolt per decade. So this is what we call the first switch degradation. Now, if we see with subsequent cycles, that is we apply about 10 power 3 cycles, and we see that the SS has further degraded. Now, let us see if this degradation comes from switching the device or simply from voltage application. Now we see that again, if we apply initial read operation, we have again low SS IDVG curve. We have an SS of about 70 to 80 millivolt per decade. But after we apply the very first right pulse, that is a negative unipolar pulse, we see that the SS has significantly degraded. But upon subsequent cycling, we see that the SS stays relatively flat. So in the bipolar switching case, we saw that we had the first switch degradation, and followed by that we also had cycling degradation. But in the unipolar case, we see that we have an initial voltage, upon initial voltage application, we have an initial jump in the SS value, but further unipolar stresses does not increase the subthreshold swing significantly. So, regardless of whether it is a bipolar pulse applied or a unipolar pulse applied, the first switch degradation is still present. Similarly, with positive unipolar pulses, we again see a similar increase in the subthreshold slope as we apply the very first pulse. And subsequent cycling does not affect the subthreshold slope of the device. Now, to further confirm whether the effect arises from the bipolar switching effect or from just the bipolar voltage application, that is, does the polarization switching matter to this or not? In order to do this, we looked at the same bipolar stress under a MOSFET. So here we do not have the ferroelectric layer, the head-Z layer is dielectric, and in this case, we neither see the first switch effect nor the cycling degradation. So we know that these effects, that is the first switch degradation and the cycling degradation, is unique to the ferroelectric layer being present there. So now let's summarize all of the results that we've seen so far. We have the FEFET in the unipolar, positive and negative unipolar cases. We have FEFET under bipolar case and the MOSFET under bipolar case. The blue bar represents the pristine as fabricated state, and the red bar represents after one cycle, and the blue bar, dark blue bar, represents after 10 power 3 cycles. So what we see is that in the FEFET, under unipolar and positive unipolar, negative unipolar, and the bipolar case, we have the first switch degradation. That is a significant jump in the value after the very first pulse is applied. But the important thing to notice here is that in the FEFET bipolar case, we have a significant jump also in the cycling case. What is interesting to note is that the degradation that we see in the very first pulse is almost equal to the degradation that we see in the subsequent 10 power 3 cycles. So about 50% of the total damage seen over its lifetime, and by lifetime I mean memory window closure, is happening in the very first right pulse. This NIT over here is calculated from the subthreshold slope directly. And we see that in the MOSFET case, neither the first switch effect nor the cycling degradation is occurring. So what exactly is happening here? So in the as fabricated state, we have the dipoles in the ferroelectric layer being oriented in random directions, and that leads to a negligible electric fields being seen across the IL layer. Now, after the very first right pulse, we see that all of these dipoles are orienting in one particular direction, and that's leading to a high electric field across the IL layer. And in response to that, we see a large number of traps being generated in the IL to screen this polarization and lower the electric field across the IL. So that is the very first switch degradation. Subsequent cycling also leads to further degradation in this device. So now we want to see if there is a direct correlation between the amount of polarization switched and the amount of traps generated in the IL layer. So in order to do this, we perform an experiment that looks like this. So let me go through it. We have an initial read operation done in the pristine state. Followed by that, we apply bipolar pulses, that is a program pulse followed by a read and an erase pulse followed by a read, for subsequently increasing write voltages. So initially we apply a very small voltage and track the memory window that we see and the subthreshold slope of the IDVG curves. And as we go, we increase the amplitude of these pulses, leading to a larger memory window and subsequently tracked subthreshold slope. What we see is that as we open up the memory window, the subthreshold slope also concurrently increases. So what's happening here is that as initially we have the randomly oriented dipoles in the as fabricated state, and as we apply more and more voltage pulses of higher amplitude, more and more of the ferroelectric layer is being polarized to a certain direction. Now that's leading to more electric field across the IL, and hence as we increase the polarization, more traps are being generated to screen this polarization. So that's why we see the subsequent increase in subthreshold slope and concurrent increase in the memory window. if we look at the polarization switched using PUND measurements, that is positive up, negative down measurements, which measure polarization, we see that as the polarization opens up in the device, the subthreshold slope again concurrently increases. So now that gives us a picture of what's happening in the very first right pulse. Now to go deeper into what's happening during the cycling, we performed some charge pumping measurements on both the FEFET and the MOSFET device under bipolar stress conditions. So we did this in efforts to try and understand what's happening during the cycling degradation. So how does charge pumping work? We apply a pulse set to the gate of this device while the source and drain are shorted and grounded, and we measure the body current of this device. Here we measure the recombination current. So according to charge pumping, what we see is that when we apply a very high frequency pulse to this device, we probe traps very close to the channel, and when we apply a low frequency pulse, we are going to probe traps both near and away from the channel. So if we look at the results over here, we apply a high frequency pulse to this device across cycling, and we see an increase in the traps generated over cycles. Now, if we perform the same cycling along with low frequency pulses, we see that the amount of traps that we detect are higher, meaning that there are trap generation not only close to the channel, but also far away from the channel happening. So now if we look at the MOSFET case in contrast, we see that the 1 megahertz pulse leads to some degradation. That is, we see some amount of trap generation with cycling when we apply 1 megahertz pulses. And as we reduce the frequency, we see that the amount of new traps that we detect are not so many. That is, there is very less dispersion in frequency in the MOSFET case. So this tells us that most of the traps being generated are very close to the channel of this device. So that's what is represented here. The frequency dispersion in FEFET indicates that there is degradation near and away from the channel, but in the MOSFET case, the degradation is primarily occurring at the channel. So the difference between the two is that there is polarization switching occurring in the FEFET case, and that's likely leading to a more dispersed trap generation. So now let's look at all of the results that we saw. We saw that by tracking subthreshold slope, we saw that there is two critical stages to degradation in FEFETs. That is the first switch degradation and the cycling degradation. And 50% of the trap generated until memory window closure are generated in the very first switch. And minimizing this effect is going to be crucial to improving the overall endurance of these devices. So we see that this first switch effect is significant, and minimizing this is going to be crucial to improving the overall endurance. Thank you for your time and attention. I would like to thank our sponsors for supporting this work.